So let's get started. I hope you're well after the typhoon. I mean, hopefully there's no water getting into your home. But yesterday there's some water getting into my room, so I have to clean up stuff while I'm teaching. But it's fun. But hopefully everything is all right. So let's get started. So today's our goal is of course continue our journey on random variable. And we have, I think, covered some up to the PMF and some material on the CDF. So we continue that journey. But before we do it, just remind you that homework one, I mean, is there already. Will be due I think next week. And then we also already released the self-checking quiz for quiz 2. So it's just multiple choice question. So you can just, when you have time, you can do it. And because remember, the self-checking quiz is by attempt, so as long as you do it, then you'll be all right. So let's continue random variable. Okay. So let's go back to the idea why we need random variable. The reason we need random variable have two. One is the sample space in the real world can be very complicated. And the thing we can measure, we can observe is just only something out of it we can measure. So random variable refers to things we can measure, we can see, we can observe, we can calculate. And these are numbers, right? So that's why outcomes are actually numbers. Okay. Or right, say for example, the plane, right? And then there's many things can happen, lead to engine failure, right? Can be one engine fail or second engine fails and third and fourth, so on and so forth. But sometimes we can't distinguish which engine will fail, right? Just observe how many of them, right? Don't know the cause. So in that case, random variable is something we can see. And secondly is to deal with the sample space, the original one can be not really needed because it's too complex, right? Remember the example we gave is total content times and number of outcome. There will be about 1,000, right? 1,024, right? It's very complicated. But if you care about just some of the head or some of the tail, which you disregard of how it realized, just the number of them, in that case, you only have 11 outcome, right? 0 plus 10, right? 1 plus 10, right? There's no head and there's one head up to 10 heads, so it's 11 of them. So that means that random variable is a way to do it, and sometimes it's easier. And what kind of number you can assign is called the support, right? And turn out that it is really important to distinguish between discrete and continuous. And the reason is because discrete you can handle using the high school math, and continuous require M2 math or the calculus. So since our class doesn't require calculus, so we focus on the math tools for discrete, and everything we said about discrete actually carry over to continuous. But if you go further, you will see that difference between the two. And for discrete, the usual case is that integers, right? What we can observe is counting 1, 2, 3, 4, 5, including 0 sometime. And the example is tossing a coin, right? Your head or tail. Instead of head or tail, we get number of heads. And in that case, there's no simplification of the sample space because it's still 0 and 1, which head or tail. So in that case, you can see the mapping. This is what we call, right? The mapping or the function, the random variable is like it's very trivial. It's 1-to-1, right? But in the case of you have two coins, tossing or toss the coin twice, then you have head, tail, tail, head, and tail, tail, and head, head, right? The 4 outcomes. And if you care about number of heads, that means that you only have 3 choices, 0, 1, or 2. That means that looking at the graph is you reduce the number of outcome in the sample space from 4 to 3. So that is very important idea, from 4 to 3. And as we said, if you have 10, then you have 1,000 boiled down to 11, right? So that would be something, a way simplification, okay? And if you don't like integer to assign, sometimes you actually need a number, right? Say stock price, temperature, wind speed is a continuous random variable, right? And yesterday I was teaching during the Typhoon set number 10. Then actually I give example which fit very well about the discrete choice, discrete a random variable, right? You have Typhoon set number 1, Typhoon set number 3, Typhoon set number 8, 9, and 10, right? Of course, in this case, this is not the sample space yet because you have no typhoon. So you have number 0. So this will be a complete sample space for the typhoon and they're all number, right? Of course, is it number meaningful? Yes, right? So that is another way to think about the problem. Okay. And as I said, it's temperature and stock market. When you use decimal numbers, fractions, these are the things that continuous random variable would make a lot of sense. So as we said, when we last in the class is we start with the discrete random variable. And the first thing to do is to describe it because we know what number can be by the support, right? What the random variable, what the number they can be, right? So to describe it, you have to tell what kind of probability for each number, right? That is this probability mass function. Is you give the number, I give you probability, right? So that is what it is. There's nothing new there, right? But do note the name is sometimes called PF and PDF, okay? PDF is not the file that you are using all the time, but that's the function. So toss a coin 2 times, so toss coin 1 times, and you have number of head, you have 1 or 0, right? And 1 is respond to 1 head, and tail is lone head, 0 head. So you can easily write this into the function because it's very likely. So if your number is 1, is 1/2, 0 is 1/2. Okay. So you can easily, if you remember, this is correspond to this graph on the left, the graph on the left, right? 0 and 1 is just 1/2 and 1/2. And the other way we have is called the cumulative distribution function. It's asking not exactly what probability you have this number, okay, for a particular random variable, but rather we're asking what probability that the random variable equal to that number or less. Okay. Or probably you ask, why just less? Why you can go to more? Yes, we do. That is called survival function, and that is not often used in statistics. There's sometimes also called survival function. Is more used in insurance and actuarial science. Okay, but they're same thing, right? But turn out that this is has nicer property of integration. We know we integrate from the left hand side, not from the right hand side. So that is the reason why less than later you will see why we define that. And this is not as natural as the probability mass function, but as we said last time, this is the most intuitive when we talk about continuous. Okay, but let's now develop the intuition behind. So toss a coin. It was 0, 1. Okay, this P already developed. We know this one already. Okay, so the new thing about this example is this line F. Okay, F is something new. And F is asking us, say F of 0 is asking, what is the probability that the random variable is equal to and less than that value? Okay, and it's only one case is only 0, right? So that's same as what you have in the P. But asking the question of F of 1 is asking how likely that the random variable is equal to 1 or less. Then what you're going to do is go up, pick up 1, and look at it before. Okay, so go up and go before. So basically, it's a stacking problem, right? Just you go up and see what is before and stack it up. So that's why I do it in the graphical manner like this, right? So we just, in this example, Now look at the right-hand side, right? If you look at f of 0, go to the P0, just put it there, and try to check, is anything less than that can be stacked? Nothing, just okay, you are done. And the next step is go to P number f of 1. F of 1, you will just look at P1, okay? And just put it there, okay? Once you stack this one, and then you just look at the thing before it, okay? And before it also stack up, okay? And stack together. And look at before, there's nothing, that's you are done. So we just look before and stack it, okay? So you see from P to F is stacking. Just building a tower in your kindergarten. I don't know whether you're a kid, you like to build a tower one by one, stacking up the wooden blocks, right? Block building. And sometimes you're a naughty kid, comes in and just you build a tower, you just spam it and just destroy, right? That's what you do from F to P, right? It's like Godzilla or a monster, just kick it out, okay? And kick out the difference between the two will be this guy, right? So that is the idea. You unstack and stack it, okay? From P to F and F to P, they're the same thing. So there's no difference between the way described. And for discrete, P is the most natural one. For continuous, later you see F is more natural one. Because as I said last time, P for continuous is always 0 in generic case, because how likely that, suppose you want to throw a dead bear to the board, how likely you end particular point? 0. You pick a number from 0 to, between 0 to 1, there are many number. Exactly the number comes out, accordingly, that will be 0. Okay, just like imagine this. Okay, maybe the simple case. Imagine, look at your hair. Suppose you have hair in your head, right? Unlike me, maybe I have some hair loss, but you guys have a lot of hair in your head, right? You think about one particular hair. You close your eye and pick particular one. We will pick the same. So suppose you pick this one. Okay? Close your eye again, pick again. Do you able to pick the same one? Very difficult. Same idea here. Okay, I hope I answered your question. Okay. So this is another question about the toss and coin twice. You have head, tail, head, and tail. All right. So now we just care about number of head. So we simplify the sample space by head is 2, tail is 0, but head, tail are 1. Okay. And what is the P? Is how likely they are. It's a fair coin. So every outcome has 1/4, right? Each outcome is 1/4. Okay. And head has 1/4. So that's why probably 2, P of 2 is 1/4. And P of 0 is also 1/4, right? Because of P of 0 is asking probability of tail and tail, which is 1/4. And P of 1 is 1/2 because of head, tail, and tail head. Okay. So if you see this is the case, then now you understand why we have F. F again is what? Look at P and go back. Why F of 0 is 1/4? Because you go up. Okay, you are stacking. So this one, 1/4, and go to left, that's nothing. So that's why it's 1/4. Why F of 2 is 3/4? Because to go up is 1/2, and go to left is 1/4. So add up 1/2 and 1/4 is 3/4. Lastly, why F of 2 is 1? Why? Because go up is 1/4, and go to left, you have 2 number, add together, then it's 1. So now I tell you how you go from P to F. Now, if you I give you the F instead, you can go from P as well, right? So you can see if I only have this F, how can you go to P? Okay. First is why this P is 1/4, because just go to down there. Okay, that is that case. And why this is 1/2? You take the difference, this guy, right? Because actual difference is this minus 0. This minus this give you this guy. And this minus this give you this guy. So you can freely switch between P and F. If I give you F, you can do the P. I give the P, you can give you F. They're the same thing. Is that clear? Now, this is the graphical representation of what we have seen, right? But let's go again. This is P, we have explained already. Why? Because this is head, head. This is tail, tail. Why this is 1/2? Because it's tail, head, and head, tail, right? Each outcome is equally likely with probability 1/4. So that's why you have this. And then how you get from P to F is stacking, right? Look at the first one, why is 1/4? Because you look at this and less, that's nothing. And why this guy is 1 is a 3/4, because you go 1 is look, check what's here, move to here, you get here and move to here as well. So stack it up. That's why 3/4. And same as below, right? Next one will be why this is the case. You go back to here, you pick up everything, stack together. And remember, if you take the F difference, you get a P as well. Okay. The difference between F1 and F2 is the P2, right? And if you take a difference between F0 and F1, give you the P1. And F0 and anything beyond that, that is become a P0. So that is the same thing, okay? Hopefully I convince you this is the case. Is that okay? You should be able to swap between P and F, right? Now, let us consider a more interesting case. It's rolling a die, and the die is have 6 faces, is equally likely. Then equal is easy. The sample space is actually 1, 2, 3, 4, 5, 6. Okay, and probably ask, what is different between this 1, 2, 3, 4, 5, 6 and this 1, 2, 3, 5, 6? Okay, and in fact they are somewhat different. The sample space 1, 2, 5, 6 is 1 is actually not a number, but 1 is saying that the number 1 is facing up. Roll a die. It's not a number. It's an outcome that 1 is facing up. But we say number facing up, we put number 1 to it. Okay, although math looks no different, but they mean different thing, because I'm just lazy here, not right one. But 1 should be saying that number 1 is facing up, right? So, but I mean, I can conveniently write this as this 1 is different from that 1 here. I hope it's clear. And we have equally likely outcome, so everything is 1/6. Okay, and you can imagine that you can have an unfair die, then it will be a little bit different, but just make sure everyone is 1/6. And you can easily construct from P to F, right? The first one, 1/6 is coming from looking at what is above, and you add the left hand side, there's nothing there. So on, the next one is Y26. You go up and add back what is before. Okay, so and so forth. That's why it's 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, and 1. Is that okay? I don't want to be too repetitive, then this is okay. Okay. And let me show the graph, right? This is the case. Because 1/6 actually this 1.16, right? Because this is 1/6, right? 0.167. So that's all the number is. Okay. Now this is nothing new there, but rather I would point you to this technical graph. You may ask why I do that, right? Remember, this is a function. Means what? A function means I give you a number, you give me probability, right? So if I ask, what is the probability of random number equal to 1.5, right? So how likely that you get a die is 1.5. There's no phase is 1.5, right? So the probability will be 0. So that's why this is 0, right? 1.5 is 0. Right? So how likely the random variable equal to 2.5 is also 0 as well. So that's why you write a line here which represents 0. And an empty circle means you should look this number rather than this one, right? And this is the graph that you will see from the stat department. I put it here is because those of you who want to study statistics beyond or go to more advanced class, they will be surprised to see this, right? But do note that this is no different from what we have in this diagram, because when we say bar chart, right, we already mean that other than this number are all 0 already, right? But this is more explicitly telling that these are all 0. Okay. In case you are not sure, but this is what you see in stat textbook. This is you will see in business textbook. So I just put there in case you would try to, oh, wait a minute, I see that textbook, they teach different thing. Yeah, because that's the textbook. We're in business school, so this is the graph. But need to tell you, because if you go to stat department, okay, you should remember this table, this graph, not this one. Otherwise, they will say I teach wrongly. Next, same, you can see the cumulative table is also going up in this format, right? But again, this is not entirely right. It should be look like this. Why? Because 1.5. Great. Probably less than 1.5 is 0, but probably less than equal to 1.5 is not 0. It's same as 1, right? Because less than 1.5, the only thing you have is 1, right? So that's why it's a flat line here. Until 2 to jump up. So that is called a step function to go up in this way. So this is, again, it's a technical. So if you're not going to stat class, you're not going to any other stat anymore probability class, then you can forget about it. This is sufficient for that purpose. When we draw this, already in our mind is that actually it is in your mind. Okay. But we're being lazy. Okay. Because business school, so that's okay. All right. So we have some room, right? Some room to say we are not really serious, but anyway, what's relevant is right. That's okay. Is that okay? So now you learn 2 ways to describe a random variable. But the problem is, okay, this graph is a complete story, either P or F. You give me the P and F. I know exactly how the random variable will look like, right? We can say how likely one happen over the other. All right. But the problem would be the P and F can be so complicated, we can't really know what's going on. Right. So just like in the chapter 1, I give the data, right? The data is speak for itself, right? So why we are, oh, I teach other class, so they said the video is record is ready, so not our class. So the question is, we have data, then your boss will ask, tell me about the data, right? Then the thing you give is mean, okay? That's what we're doing. And later we'll say, how good is the mean is the variance, right? So this is what we do. We give you a random variable, right? Random variable, we have the full description for the P, right? The P function or F function, right? But the P function is so complicated, we don't want to do that, right? So what you give the boss is give you what is expected value, right? So that is the best thing to say, okay? right? So what is the expected value is mean. What do I mean by here? So let me draw a picture. So suppose the sample space, there are many outcomes live here, outcome 1, outcome 2, outcome 3, right? Many outcomes, right? And the outcome can be roll a die, toss a coin, whatever, right? And our random variable x will tell us outcome 1 will map to some number. I don't know, but say 99 or 100, whatever number you want, call x1. And this map to number x2, right? Number x3, whatever number, right? This is called random variable, right? And in the original sample space, you give some probability, right? Probability 1, probability, some probability, how this happen, how this happen, and how this happen, right? Some probability, P1, P2, P3, right? This is what we had. And the big P will tell us how likely is this probability, right? Right? Maybe I just make it a little bit more interesting. So maybe sometimes just this map to this one as well, right? Then the probability of x1 is just P1, right? And probability of x2 is just P2, right? Plus P3, because they're two outcomes, right? So this is what we have, right? This what is the overall picture, right? The left-hand side here is we know this P how to describe. This is come from the data, follow the axiom, there's scientific knowledge, we get the P's. And the big P's are telling us each random variable number, right? From this P, how we add up, right? This is the big P tell us. And the next thing is, as I said, you don't really want to say this because this may be a lot of value. You give this big P is not going to be super helpful for the boss to understand what's going on. So we want what we call expectation is the following. Remember the idea of random experiment. Suppose we have this hypothetical experiment many times. We run this many times. So each random experiment, according to this probability, some outcome will comes out. Okay? And you see x1 here. Right? If O1 comes out, it's x1. If O2 comes out, you see x2. If O3 comes out, also is x2, right? There will bunch of x1 and x2. Right? That's another thing. There's x1, x2, 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 and x2. And x1 will have P1 likely comes out, x2 where P2 plus P3 comes out, right? So if you have, say, suppose P1 is like 0.5, or maybe 0.4, right? This is 0.6, for example. That means that if we have 1 million times, suppose I want 1 million, maybe easier way, 10 million, right? 10 million random experiment. Then 4 million will be x1, okay? And 6 million will be x2, right? So what is the mean, right? So we have 4 million x2, sorry, 4 million x1, and 6 million x2, right? So average will be 4 million times x1 and 6 million times x2, right? And divided by 10 million, all right? And what's this? Look carefully. 4 million over 10 million over 4 million is actually P1, right? And 6 million over 10 million is P2, right? So that's why the mean of this hypothetical experiment, right? You run the experiment of data, right? Your data, that's the data, right? You have 4 million x1, 6 million of x2. Remember, these are data, so you can calculate average. And is this mean of the data is simply probability times the outcome. So simply the mean is just P1 times x1 plus P2 times x2, right? So the probability time is value is the mean. Okay, that is what we call expectation. Okay, Let me repeat what I'm doing here. The expectation is simply the formula, so it's simple. The probability time is the value you do for every single value. Every value, you multiply the probability, add up together. Okay? But you ask, what's this? This is rather trivial, right? Why it makes sense? It's because of we repeat this experiment many times. How many times appear is actually the probability is equal to the relative frequency, right? This is actually, we learn the first probability definition, right? Probability by construction, if you follow the random experiment, something can be repeated, right? Is how likely that in terms of ratio, right? How many times repeat, how many times favorable to the outcome, right? It's a ratio. And that is probability. Right? So now actually we go back to the circle, right? Although we learn new probability, but we use the way about the old way, right? Because imagine that this thing can happen many, many times, although we don't, but imagine hypothetically, imagine many times, and the number of times it appear should be according to probability, right? So that's why this expected value is, imagine that we run this experiment many times, and you will see many outcome, and you use the random variable to convert this outcome to numbers. That means that you have a list of numbers, and you calculate mean of these numbers is our expectation. Okay, I hope it makes sense. But so this is the meaning, right? You take any number, every number you can take, multiply by probability, add them up. Okay, and just other example again. You toss a coin. Okay, you have 0, 1, right? Because number of head, right? And they're equally likely, right? Suppose you toss a coin 1 million times, okay? And half of them is 1, half of them head, half of them tail. That means that half of them is 1, half of them is 0. So the average of this number is 1/2. Why? Because you have 1 million of 0, half million of 0, half million of 1. That means that 0 times half a million, 1 times half a million, and you divide 1 million, right? Half a million divided by a million is 1/2, right? This is actually probability, right? So that is going back to the circle. Although we say probability applied to things can't repeat, right? But when you actually go back to the definition of expectation, is go back to the idea of you can repeat things, right? Although in principle it can't repeat, but in theory you can repeat, right? In your head. So let's see the example. Probability of head, okay? And this is a fair coin, so this is given to you, right? This is a random variable. We know this P. Okay, this is given. So this is a complete description of the random variable is X and P. Okay. And now we want to know the expected value. Remind you what does that mean is, it means that if you say repeat this experiment 1 million times, you should have 500,000 0, 500,000 1. Okay. What is the average of this? Okay. You don't have to do 1 million, but you just simply multiply and add, right? 0 multiplied by 1/2 plus 1 multiplied by 1/2, right? So that's what it is 0.5. So since it is a mean, this 0.5 doesn't mean that you toss a coin, you have a half a head or half a tail, but simply means that it's a mean, right? What does that mean, the mean? Mean is middle by construction. What does that mean? It means that suppose the data here, 0, 1, right? And if you run 1 million of that, you have a 500,000 0, 500,000 1, right? By mean means that you are exactly in the middle, this 0.5. Look at the left-hand side distance and right-hand side distance. Add up together, they're the same. And 0.5 is exact location where left and right are the same. Okay, that is the meaning. Okay, so it boils down to the question, is the mean meaningful? Right? The mean has to be meaningful if the distance makes sense. Right? What does that make sense? The example for this may make sense number of head. You can say 0.5 head. That means that maybe you run 10 head You run 10 of this, 5 of them are head, 5 of them are tail, right? But what does that make sense when we say the example of typhoon signal, right? We have 0, 1, 3, 8, 7, 9, okay? And when I have, say, the average is like 5, what does that mean? Why does that make sense? Because the typhoon number are not numeric data. They're ordinal. Remember, ordinal is order matter, right? The higher the number, I forgot 10, right? But all the order matter, right? 9 and 10 is not the same as, oh, there's no 7, right? Sorry. My my knowledge is wrong. Is 1, 3, 9, 10, right? So, I mean, the difference between 8 and 9 and 9 and 10 are not the same, right? And 1 and 3 is not same. 0 and 1 is not same as, it's not the 2 times between 1 and 3, right? So when you calculate mean of this ordinal data, although you assign integer there, this doesn't make anything sense. So if your random variable is ordinal data, then you calculate mean, basic rubbish, right? And probably you ask, what should we do there, right? Then you can ask something like median idea should be there to calculate, but forget about this because our life is so short, so just focus on this numerical thing. If you want to have an ordinal data, how can you calculate this is another issue, okay? We don't want to deal with this at the moment, but this is okay, okay? So we just forget about this typhoon thing, I mean, but I hope you understand why it doesn't make sense when you calculate expected value for a typhoon. Because the number is not, the difference doesn't make sense, right? Because this is the, remember what we're doing for expectation, it's the mean. For this calculation to make sense, mean has to make sense. If mean doesn't make sense, you're calculating rubbish. Okay? So same idea, you can calculate the expected value of a die. Okay? Again, this is the P. Okay? This is fair die, but if you give unfair die, the same idea, right? So basically, you just take every number there. You multiply the probability, each one, right? And add all up, right? So this is the same 1 times 1, 6, 2 times 1, 6, 3 times 1, 6, so on and so forth is 3.5. Again, 3.5 simply means, doesn't say the die come out next is 3.5. It's just in the middle, okay, of the number, okay? That means if I run many numbers, move the die many times, okay, the average numbers is 3.5. You run many times, okay? Just to remind you what it is, you have 1, 2, 3, 4, 5, 6, okay? Your actual number is here, the mean. You have many outcome if you run many times, okay? And 3.5 never appear, okay? But 3.5 is just at the middle of left and right, okay? Just to make sure that you understand, okay? So that's why we have to emphasize is for numerical data. So the random variable, to make sense, when you calculate this to be sensible, the number you assign is to be meaningful. You can't arbitrarily assign, okay, number there. If you make a arbitrary number, you cannot calculate expected value. You can still say about the P, that's fine, but the mean is not, or expectation is not going to be meaningful at all. Okay, is that clear? So just to remind again, expected value is you assume you run this many times, you get all the data, you calculate the mean of the data. Okay. So before we break, I want to talk about this, what we call linear property of expectation. Okay, and this fits our intuition very well, and it's very natural and used many times in investment class you will learn. So what do we have here? A random variable, I multiply by A is a constant, means a number, means 1,000, 5,000, 105,000 is a number, and number 2, and number there, not going to change. So it's a fixed number there. X a random variable, we know what's random variable. Random variable is a number that are assigned to an outcome. Okay, it depends on what outcome comes out from the random experiment, and is equal to A times this guy. Okay, you just why this thing is true, or what is it useful? Very simple. Consider finance application. X is price of one stock, one share. Okay, price of a share of a stock. Okay, A suppose 100 means that you hold 100 shares of that stock. So expected AX is a portfolio that contains 100 shares of that stock. What is the expected value of that portfolio? Will be 100 times of a single share. Okay, why is it important? Because we don't need to track portfolio. We only track the single price. We don't need to, for each size portfolio, we need to model it. We need to model a single share. That's sufficient, right? So that's why when you look at investment, we look at single price, not look at the whole thing, right? Next, this thing is easy to understand in investment as well. So suppose you X, you plus a constant number, is not where we is. It's just simply just expectation of one thing plus this. Okay, what's B? Imagine B is a portfolio, a stock. Okay, one stock or many shares, doesn't matter. But B is cash. This is stock plus expected value of stock plus cash is expected value of stock plus cash. If you're cash, you can separate them. You don't need to care about the cash. Okay. Why? Because cash is not changing. Okay. And you can separate them out. Okay. A portfolio of stock and cash, it just the expected value is expected value of the stock component plus the cash. Is that clear? So this is what we have. If a portfolio, I have 100 shares of a single stock plus cash, it just 100 times the expected value of the stock of single share plus cash. So this is exactly what it means, right? And it's very convenient. And you may ask, why I need to list this? Isn't it intuitive? No. The variance doesn't follow this formula. They exactly doesn't follow for this for variance. We'll show you after the break. Okay. But this is, I hope this is very natural from prospective investment. Okay. Because that means that I can divide and conquer, right? If that something doesn't change, then you don't need to worry about it. You multiply something, you just forget about the multiplication and take it out. Okay. Now, as we said, we have a break, so let's have a break of 15 minutes. In the meantime, I guess we do the usual you reply thing as attendance and participation. So I will see you in the 15 minutes later. It's 2:32. 33. Oh, sorry. 2:33. I come to the class, so some people. Hope that you feel happier with the break. Okay, there was some small gift from me. I mean, if you need more, just feel free to take. So let's see, what do we have? Nothing. Is it raining? I really don't know. I've been indoors since 9 a.m. in the morning and teaching, and then they're not going out. Yes. Yes, I think the formula is very intuitive, I hope. Yeah, listen is easy. Oh, very happy. When is final exam? I guess the TA sent you the email is like, I think the final exam is on the 27th, Friday, Thursday night. Only 1 hour exam. So it's like, I think 6:30 to 7:30, something like that. It's 1 hour. And if you have any legitimate reason cannot do it, we will do a makeup for you. But makeup have to be after, not before. Okay? So that is the only thing. I mean, of course, you have some reason you cannot attend, then just send a TA. We can centralize arrangement for a centralized makeup. But hopefully we can only do 2. But if very rare case, you have to do more. But that would be, hopefully we don't trouble the TA that much. But let's hope we don't do too many. But a bit confused, hopefully. But you can ask the question, because this is something I can't help you. You have to say what is confused. No, I'm not confused on the day. Oh, but that is a little bit funny, because sunny and raining. And probability, yeah, means to make sense, otherwise rubbish. That's very important, because expected value have to be applied to numerical data. So if your random variable is ordinal in nature, then this is a crap. Okay. One key point. That's very good. I remember there's a very famous statement. Is write 5 words that you know, then right? Write 5 words you know, and then there's a 5 plan is write 5 words you know. It's an English exam, but anyway, this is exactly what's going on. Right? And I think there's another very famous, right? Very famous question is find X and something like this. X, and this is right. And find X, the answer is here. I think this joke, right? It's the same joke goes on. Find one key point is the one key point, right? It's doing exactly what it's doing right now. Yeah, the speed is okay. I guess the mean is 3.8. Again, right? This is ordinal. So the mean is not very meaningful, because 4 and 5 and 3 to 4 is not, the distance not the same. So what's in the middle is not too meaningful, but it does mean something, right? It doesn't mean a lot, but it still have something to say. But I don't take this too seriously, right? But I would just look at the chart. Okay, they seem to be okay. Oh, I didn't know that. I didn't take a bus, to be honest, so I never don't know. When we will have the next typhoon holiday? According to data, October is still possible, but November is not possible. So next, maybe we should have one holiday next month. Usually October is half of the September. So if we have 2 typhoon holiday in September, we should have 1. Expectation, right? And expected value is 1. If you ask me, that is my okay. Thank you, but that's what my doctor said. But anyway, but whatever is okay. Is there any no more question? Then I'm done. So let's continue with this linear property. So let's see the example, and then we go to variance quickly. So look at this stop price. No longer we have floating a coin and die, right? So this X can be 1, 2, 3. PX is 1/2. 1 quarter, 1/2, and 1 quarter. So if you remember, actually this is total a coin. The total coin is a 0, 1, and 2, right? In that case, right? This is head, right? This is tail, and this tail head and head tail. But in this time we have, but in this time we have 0, 1, 2, but we have 1, 2, 3. Why it makes sense? Maybe the stop price now is 2, right? If 2 days, you can go up and down, tail head or tail head, up and down or down and up, remain at $2. If you go up, it's 3, right? Or you go down, then it's 1, right? So And that means that we have this guy, right? So each day it can go up by 50 cents or go down by 50 cents, right? You go up by 50 cents, 2 times you become $3. You go down by 50 cents by 2, that's 1, right? So head means go up by 50 cents, down, tail means go down by 50 cents, right? So you can have 1, 2, 3 outcome, starting with $2. So you go up by 50 cents, go down by 50 cents, 2. So this is, it can be modeled in this way, okay? And as I said, this is actually how you model the stock option, right? It's binomial tree. It's exactly this one, but do it very big one. So let's see the expected value, right? The stock. So it's equal likely go up and go down. So without calculation, it's actually 2, right? But you can say is half of time has $2, 1/4 of time is 1, 1/4 time is 3, so you have $2. So there's nothing way deep goes on here, right? But now let's do the question of, this is a price of A share. Well, how about we have 100 shares of that stock and we have $300 cash. That means that this portfolio can be represented by this, right? 100 shares and 300 cash. First thing to do is expectation. You can separate cash and money, cash and stock, right? So cash is here. Okay, stock is actually, this one should be, if you want to slow down, is 100x, right? Plus 300. You go down first, right? You separate the cash and the stock. And 100 shares is same expected value of 100 shares portfolio is 100 times of the 1 share. Okay, and it's 2, so that's why this portfolio expected will be 500. Okay, so that is the expected return. Okay, that's we learned in the investment class. This is what you learn. The first class, I mean, first 2 classes. Is that okay? Now, next is variance. We know why we want to talk about variance. Variance asking us how good is the mean, right? Is okay. If variance is large, mean is not good enough, right? And the calculation of the variance, if you remember, is like this, right? Variance of X is adding up each observation minus the mean and square divided by n, right? I mean, you still remember this one, right? If you have samples minus 1, right? But we don't have, we were about the sample because remember, we run this experiment many times. We have run as many as we want, so it's population. So we don't have to worry about this part, right? And this turned out to be same as this guy. Why? Because this is the mean, as we have said already, is expectation, right? That is what we learned just before the break, right? Expectation is the mean, right? So that means that you take any value and subtract by expectation, right? And same as when you calculate expectation, over n is just probability, right? Because remember, this is just adding x times px, right? And you recall the mean is just what? Adding all the x divided by n, right? So over n is just replaced by probability, right? Because this is equally likely up here, but this 1 over this is like 1 over n, right? Because how many times you appear, right? So this is the variance. This by this formula, you take the what value, subtract the mean expected value, and square it times probability. And as I repeat, this is exactly the variance. If you repeat many experiments, each experiment you see the outcome, you use the random variable to change the number. Okay, you get all the number from many experiments, and you calculate variance of this number series. It's exactly this exactly this one. Okay. Remind you that variance is how big the difference from data from the mean. Okay, so that is very important. And if you look at finance, this is measure of risk variance. The larger the variance, the more risky you have, right? But sometimes they use standard deviation, but same idea, right? Standard deviation and variance are the same thing. So just take a square root, right? So the variance is the risk, financial risk there. And probably learn from the first class of finance or investment, there's a trade-off about the mean and variance, right? Because we like higher mean, but we don't like variance. So in the market, it's efficient. It must be, if you want higher mean, you must have higher risk, right? That's why the risk return trade-off, because everyone wants to have high mean and everyone don't like risk, right? So if you want to have higher return, you take higher risk, right? If you're willing to take more risk, you have more return, right? So that is the idea. But I'm not going to teach you this investment class, so that's why. Just know that you know that is why we care about the variance, right? So look at this question. How do you calculate variance? It's very simple, right? You just take each number there and minus the mean. And from last example with 3.5, you take minus the mean and square it and times probability. Do the same for the rest. Look at 2 minus expectation square times probability and do the rest is 2.9. Of course, if you don't like variance, you take a square root, will be the standard deviation. But for our purpose, variance is the most useful thing. Okay, and because standard deviation is take a square root. Okay. So now I give you the reason why we need to talk about linear property, because variance doesn't follow linear property. So again, A and B are constant, X random variable. Variance of AX is not A variance X, it's A square variance X. Why? Is if you have 10 stock, right? The variance of one stock is like this. When 10 stock is way much higher, the number can be when you go up, 10 stock goes up, right? 10 share goes up. So it can be multiplied way much more because it's square. Of course, you can say if you like standard deviation, SD, right, of AX is still A SDX. Okay. If you measure the risk by standard deviation, it's still linear. But the variance you multiply by contracted, right? It's A squared. So if A is 10, right? Suppose it's 10 shares of the stock, then the variance will be 100 times. Okay. But standard deviation is still 10 times. Okay. I hope that's clear. And the next is something very intuitive. If you invest in stock and the bond, the risk of stock and cash, it's just the risk is just stock, no cash. Because assume you put the cash under your mattress, your home has no fire, same, right? Unless the hurricane go into a house and roll out all the cash, it should be safe, right? And that means if the portfolio has A share of X and B share, it's just A squared of the variance of X. Okay, so that is variance is quadratic, but not linear. Okay, it's A squared. Okay, so this turned out to be very important thing about diversification. Okay, but you see when you learn investment class this idea of A squared stuff. Okay, so let us look at the portfolio question finance application again to see the variance calculation. Why? Because as I said, variance is a measure of risk. Okay. Now we have the same problem. Well, the calculated expected value is 2, right? Because this in the middle of that. Calculate variance of this stock will be look at each number 1 minus the mean 2, okay, square it and times probability. You do this for every single entry, which gives you 1/2. Okay, is that clear? So remember, what we're doing is just you repeat this experiment many times. You suppose to repeat 1 million times. 500,000 will be 2. 250,000 will be 1. 250,000 will be 3. Right? So you can calculate the mean, which is 2, and you can calculate variance. Right? Remember, variance is like each observation you subtract from the mean and square and times how many likely you are there. Right? So it's just 1/2. So now we have 100 share of X and $300 cash. So this the portfolio like this, right? And if you are not familiar, you can do this first, right? The portfolio of stock and cash is just variance of stock, because cash has no variation, right? $300 stay there. Okay, and then go up 100 share. The variance is 100 square times the variance of a stock. Okay, so when you take out things from the variance, you do square. Okay, there's a very important operation. You will learn it in the investment class again, again, and again. Why? Because you take a square root. A square, so that's why this one. Okay, and then this 1/2, and this is 5,000. So you may kind of ask why this happened, why square. In the math, it's like this. Because everything become, you add 2 0 there, right? And the mean also add 2 0, right? That means that everything become 2 0 here. Right? Everything is have 2 0 here, 2 0 here, 2 0 here, 2 0 here. Right? But it's square. You take out 100 from that square, you have to raise to the power 2. So that's why you're 100 here. Because everything take out is 100, but the square there, take out 100 once, take out 100 twice. Okay? So the variance is 5,000. Okay? So here is some advanced thing, which we only talk about in principle, not go to math. Okay? Is so far we only use one number. We assign a number to an outcome. Okay? But very often, one number is not sufficient. We need 2, 3, or more. Right? For example, in the stock market has many stocks. Each stock would have a number. Right? Stock price, each stock price, right? Of course, if you talk about the stock market index, only one number. Right? That's simple, right? That's something we can measure. But if stock market have many, many stocks, then we have each stock with a number. Right? Potentially, that's how you measure, right? So we use multiple numbers. Suppose 2, right? Make it simple. Suppose you have stock and investment, you have stock and bond and cash, right? You can stock maybe portfolio of your stock and portfolio bond and also cash, right? Cash is not random variable anyway, right? Just stock and bond. Then to do it, you have the same thing you call what we call the joint probability distribution is X equal to some value, Y equal to other value. Okay. And if this is only X, you forget about Y, it's called marginal. And it also have cumulative join, it's same as the idea there. So you can go from here to here, they're the same thing. Okay. But you can't go from you can go from here to here. You can go from here, but you cannot go the direction. You cannot go in this direction. You cannot go from this direction. Okay. And this is not needed because this is more advanced, but you will see it are in the investment class, right? Because different stock are your different value, right? So you've seen this in the investment class, not in our class. So, but although we don't talk about that, we need to define this because this is somewhat important. Okay, we don't give you foundation, but you can imagine expected value of stock and bond can be set as expected value of the stock plus expected value of bond. Okay, I don't do the proof, but you can easily see that can be proved. And that means that you have 100 shares and say 200 bonds will be 100 times each shares of stock and 200 times each value of bond. Okay, so very natural. You agree? I don't think anyone would disagree with that. I mean, this is very natural. Or X is stock A, this is stock B. That's the same idea. Okay, two stock, you just add them up. But I think that is important about this variance sum. Okay. Now, you will see this variance sum. It's not surprising. Is variance of the sum is sum of its variance. But with important caveat, they are independent. This is only true if they're independent. So if they're independent, the risk you can divide and conquer, right? If the variance but if that's not the case, sorry, it's not independent, then this is not true. Let's see what happened when it's not true. Look at below. If not, what this guy? Covariance. The meaning is exactly the same as what we studied in the first lecture. Is how they're related. Are they above the mean together or below the mean together? Okay. Remember, covariance can be positive, can be negative. So the variance, the sum, can be more than sum of the variance, can be less than. Okay. We call variance a measure of risk, right? We want it as small as possible. So we want to find investment such that this is negative, or at least not so positive, right? So that is called diversification. Why? If you put all the egg in the same basket, the covariance is very large, right? Because if one break, all break. If one break doesn't break, right? Covariance is 1. All right. If they are negative, they are uncorrelated, then it's diversified portfolio, right? So that means that the variance is less. Okay. So that is exactly why in finance you want to find a investment that are not correlated, right? That's why people invest in Bitcoin, invest in gold. Why people in US want to invest in China, in Asia, and Japan, because they are not so related to the stock market. Why people invest in antique? Why people invest in art? Because they are unrelated to stock market. That's the reason. So if they're not independent, how they're related is very important. And that is the reason why people make money in finance. Is how to find investment that overall have lower risk by looking at the investment such that the covariance is small enough. Of course, you have to minimize this as well, but finding the smallest covariance is very important. Okay. But let's go back to example. You look at this. In our class, we focus on independent, okay? But remember, independent is very special case. In general, it doesn't hold. It's not independent, right? But in our class, we just make it simple. And you should remember that in the investment class, everything is covariance related, right? Otherwise, investment class is very simple, right? There's no need to do anything, right? But now we are going to look at it. So at least you will ask, if independent, what can be done? Still, you can see the trade-off between risk and return, even in this case. Okay, so let's see. So consider the case you have stock X and stock Y. Stock X has mean return of 1%. Variance is 5.05. Y is 0.05. Variance 0.01. Okay. Consider the case, simple case, you can change the number. Z is 0.5, 0.5. So half X, half Y. In this case, what you have is the portfolio Z will be half of X, half of Y. The expected value will be half of X, half of Y. That means half of 0.1 and half of 0.05, which is 0.75, right? One is 10%, one is 5%, right? Average return of portfolio with half X, half Y is 7.5%. Is that clear? Now, if they're independent, the portfolio variance will be, because independent, variance sum of the variance. Variance of the portfolio, which is 0.5x, 0.5y, will be variance sum of the variance of each part. And here is the important part. Here is 0.5. You take it out, become 0.5 squared. Okay. Once you take it out, the variance is only 0.015. Okay. So this is, if you are the financial planner, if you divide it in half and half, this is what your return. All right. You can see the stock X, has higher return, also higher variance. Stock Y has lower return or lower variance. So if half and half, you have half return, but somewhat high, little bit higher risk. So you can decide, depending on taste, you can change the number, right? What is the optimal weighting of the X and Y? Depend on the taste over risk and return. But you tell me your taste, then the planner will tell you what is the appropriate mix. So this is the basic class of investment, right? Finding the best combination of return and the risk. Okay. Of course, I didn't talk about the covariance. If you do the serious stuff, you have no covariance, right? In the past, how they move together. Okay. So this is actually the investment class. You will learn it in the investment course, how to find out the optimal mix. There. Is that okay so far? So just to repeat what we're doing, because from that on, we are learning the special cases. So the general theory of random variable, we learn several things, actually 4 things. First, we learn big P. Big P is what? Tell me the number, I give you the probability. That's it. And then second thing is big F, is you give a number, I give you a probability equal to this and less. Second. Number 3 is the mean, because you give me P and F, it's complete, but it's too complicated. I want a single number to represent what may I expect the number to be. There's a mean with expectation. Okay, the calculation is the value times probability, the P, and add them all up. The last thing we just learned is a variance, which is a measure of risk in finance as well, because it's how good is the mean, right? How the number is different from mean. The calculation is each number, subtract the mean, square times probability. So there's nothing new there, right? And this is measure the risk. And then also went about bivariate, we have two number there. Mean still the same, very easy. Just you can divide and conquer, separate them because linear. That's why no need to worry about things. Variance, you can still do the linear. Separate. Linear means variance sum of the variance, but it's only true when they are independent. And as I told you, in general, it's not independent. There's very few things in the world independent. Okay. Rather use this one. So as we do, right, we try to observe different investment, right? Look, I don't know, but you guys don't have MPF yet, but when you try to work out, you would be investment or retirement fund in different type of fund. Can be go into the fund in US, fund in Europe, fund in Hong Kong, right? So that's why you want to invest around the world. One reason is if you work in Hong Kong, your job is subject to the risk in Hong Kong, right? So, but the risk in Europe or in US is not so related. Okay. In general, that's why you want to invest around the world. Okay. But anyway, let's talk about the following. Now we learn random variable, right? And of course, for what? Why we learn this? Because this is by itself, without talking about data, by itself is useful for modeling the future. Okay? Although we are not able to use this to measure how likely the typhoon holiday is going to come out, okay? But at least you will see this is very useful for many business applications. We can guess how many customers will arrive in next hour, how likely that we have holiday, maybe typhoon can calculate that, maybe follow, maybe Poisson, there will be something, we'll talk about that, don't worry. So there will be some application to this common discrete distribution. Okay. As later you will see, the continuous one is a bell curve. Okay. But in discrete, there's something that something bell curve is related. So later you will see the binomial is very close to the bell curve. Okay. This is the bell curve idea. And hypergeometric is very close to what when you have to do accounting, you do audit or quality control is something we have this one. Okay. And this is something like measuring how many customers arrive in next hour. Binomial is asking something like how likely that the stock is going to go up in how many days. But it will be made clear. Okay, but we start from something very simple, uniform, which said each outcome is equally likely. We start from that one, and then we go by that. But these are all special case and with some special application. But do note that I say common and also very easy. I pick 5. But if you look at Wikipedia, you will have more than 100 or thousands of them. And each one will have its own application. And in particular, you will see each one have the use cases. And actually, this arrives from physics, right? Because many things that will follow certain distribution. Okay. But let's see what we can cover today. So let's cover the first one. Uniform. Okay. And uniform is so easy. Actually, we have been doing it all the time, most of them. We assume every outcome is equally likely. So if your n outcome, then each one will appear with probably 1 over n. Okay, and the way x1, xn can be any value, can be 1, 2, 3, 4, 5. Consecutive number can be any number you can think, as I said, is the typhoon signal, right? 0, 1, 3, 5, 7, 8, right? And the probability function is very simple. It's a table, right? Each number have probability equal to 1 over n. Okay. And this satisfies many classical cases, right? In the gambling, number ahead, tossing a fair coin, rolling a fair dice, right? This is something very natural thing to happen. And very often, although we don't talk about this class, but if you still remember Bayes' rule, right? Bayes' rule, you start from prior, you learn some information, you can bump posterior. The question probably you ask is, where's the prior? How can we have prior? Usually when you consider case. The prior in general, if you don't have no idea, uniform distribution is our prior. And we learn new information, we update our probability, it becomes a new one. Okay? Uniform is something that we don't know what happened. That is a very standard thing. Start from the uniform. And base rule will tell us what the next. You keep learning until you get a P. So that's what we do, right? Remember what we learned this, just to recall, this 5 structure is a special case of the P, right? Because what we learned is general P. But now if the P, just like the example right here, everything is the same, that's called uniform. Okay? It's a special case of what we have. Okay? For example, X is 1 up to 5, the P looks like this. Up to 3, 1 to 3 look like this. Okay? There's nothing new here. So I still have 3 minutes. Okay? It's Bononi. Okay? But I just talked about this a little bit, but Bononi is probably the first distribution invented by a mathematician. It's very simple. Just consider 2 cases. 2 outcomes is either success or failure. Just once. So just basically toss a coin, head or tail. But the coin is unfair. Okay? Means that success has probability P and failure 1 minus P. Okay? So that means that if my random variable is number of success, this is our P function. Very simple. Just 2 outcomes. One is success, 0 is fail. Success is P and fail 1 minus P. Okay. And the support is 0 to 1. And P of 1 is P. P of 0 is 1 minus P. Okay. What this is tossing a fair coin. Okay. Or unfair coin is also okay. Right? Because P can be anything. Unfair coin is also okay. Running experiment with binary outcome. Right? Basically, what they're doing is, in the world, you see it's binary. Either success or failure. Right? Either you do a business, you don't care about how much money you make, as long as it's profit, it's success. If it doesn't make it, it's failure. That's it. So it's simplify the future into 2 ways. Success or failure. Very simple. Okay, it's binomial distribution. And obviously, one last point is you can calculate the mean, right? Let's do this for the last thing before we release. Mean is what? Mean is, you look at this number, 0 times 1 minus P, right? And you do another number 1 times P, okay? The binomial distribution, the expected value is P. Okay? I will leave you for fun at home if you want to do it. Calculate variance of X. But we'll do it next class, don't worry. So, enjoy the rest of the day. Have a nice weekend. I'll see you next week. Bye-bye.